to have your slides ready and share the screen as soon as the previous speaker ends. And besides that, I don't have much else to say. The NAC has been going for a few days, so I'm still looking at my clock. It's still a few seconds to go. But we can start now. And Andrew, you're ready, so I switch off my mic and I switch off my camera. If you need anything, just go. I will be here. You can start.
Okay. Well, thank you very much. Bang on time. I will try to keep to that time. My job really today is to introduce the network and to talk a little bit about some of the, perhaps viewers, the key results that have come from the network over the course of the last year or so. And this is, by necessity, it will be broad, brief, very comprehensive. And so I apologize to you if your results that you're perhaps most interested or feature. But I've tried to give a sort of overview and a feeling for what the network has been doing over the course of the last year. So a little bit about the network. Most people here probably know this, but Network 3 is predominantly concerned with the nature of astrophysics in the most extreme of conditions, extremes of temperature, density, velocity, and so forth. And almost exclusively, those conditions are formed in and around compact objects through their formation and their evolution. And in general, what we do splits down into two broad areas, which is studies of accreting objects across the mass scale from white dwarfs to supermassive black holes, and understanding transients both across and beyond the electromagnetic spectrum. And that leads to a very broad remit, which is why what I can talk about today will really just be a taster of some of the science that we do. And of course, that will be going into in a lot more detail with some other results through the course of this afternoon. So please, if this does tickle your fancy, then please do stick with it for the rest of the afternoon. And so to kick off, this has already been talked about by people who have seen, all of the NAC so far. And if you haven't, then, please do go and look at the Access Astronomy YouTube channel, which has these talks sitting on it. And of course, one big recent result is these new insights into this exceptionally famous image of the black hole shadow in M87, and taking it from being a total intensity image into being an image in polarized light, and splitting into that polarized light. It doesn't just give you a cool new image, although this is a particularly beautiful image. It gives you a really new insight into the physics that's going on in that accretion flow and in and around that supermassive black hole. And therefore, it gives you a new way of constraining, I think, in particular, the accretion rate, but also the details of that accretion flow, which is ongoing. And I would say that was being talked about by Monica, and please do go and look at that talk and have more sort of insight you would like to have there. And so stepping on quickly, another recent result in the course of the last few weeks has been continued improving in the constraints on the neutron star equation of state. And this has been done predominantly by the NICER satellite, in this particular case, or NICER, which sits on the ISS. And it enables you to do exquisite time resolution spectroscopy of neutron stars, in particular, millisecond pulsars. And so you can really start to map out the structure of the neutron star by looking at the phase resolved spectroscopy. And this is a complex plot that I'm not going to go into the details of, other than noting the fact that you start to get really quite unique constraints on masses and sizes of your neutron stars. And so in doing that, you're able to get the mass radius relationship and therefore begin to constrain the equation of state. And so this is, really valuable insight, which is coming from, these X-ray observations, and that can in turn be, valuable on its own, and it can also be paired with additional information which is coming from other priors or other information. And so this is a paper which takes that data and pairs it with information that you can get from gravitational wave signals to get yet more constraints on the mass and the radius of neutron stars. And so these contours are still larger than we would like, and there are certainly still possibilities of having multiple different models for the equation of state which are allowed, but they are rapidly shrinking and are starting to make real progress into noting what the real equation of state of neutron stars is. And that in turn, in a sense, allows me to sort of segue into the next area of work in the network, which is trying to open up the prospects for multi-messenger astronomy. And so the equation of a state of a neutron star, of course, it's not just interesting for understanding the neutron stars that are being observed by NASA, but the equation of state of a neutron star impacts how those neutron stars behave when they are shredded, either by merging with another neutron star or with a black hole. And that in turn affects how much mass is thrown out from the system and what the electromagnetic counterpart might be to a gravitational wave merger. And so in this paper here, from Vayamaikas, Tamai and Sankei et al., there is an attempt to actually look at, what the properties of a so-called kilonova, this faint, fast transient we see, might be, really considering a wide range of physical possibilities. And so, this is, some observations which inform some theory, which then, of course, in turn inform further observations. And so, as well as trying to understand the expectations for gravitational wave counterparts, we have also worked quite hard on trying to find those EM counterparts. And unfortunately, in the COVID-curtailed 03 run of the LIGO Virgo CAG detectors, there were no counterparts discovered. But members of Network 3 were very involved in searches, and there are two different approaches that you can use for these searches. So, for example, you could pick off individual galaxies in gravitational wave error boxes, and in doing so go very deep, or you could go very wide and cover the entire error box very quickly, but at somewhat shallower depths. And so these are different complementary approaches to searches, and Paul will talk a little bit about these from MEALECT later on in this session. And so, as well as the work there being done on neutron star equations of state and gravitational waves, there are, of course, a raft of other transients that we can uncover. And perhaps one of the most exciting areas of research today is in understanding the nature of fast radio bursts. And there is a real phenomenal increase in the rate of detections of fast radio bursts in the last few years by a suite of new facilities which start to do them. And one recent result is the identification of the first fast radio burst with LOFAR. In a sense, LOFAR has kind of been left out of this in that, everything else that has looked for fast radio bursts has found it, and until recently, LOFAR has not. And so these are detections by staring with LOFAR at one of the repeating fast radio bursts and to begin to see them. And firstly, that tells you that you can see them at much lower frequencies than they have been observed before. And that's, of course, valuable in its own right for understanding what the medium around the burst is doing. But also, this particular event is one which is periodic for reasons which are not yet entirely clear, but may be related to a binary in which the neutron star resides. And one striking feature of these detections is that they low frequency FRBs, if you like, those detected by LOFAR, appear to occur at a different phase of the system than those which are detected at higher frequencies by CHIME and so forth. And so, understanding this may well start to give us real insight into what is creating these fast radio bursts. And, a prime candidate for their creation is that people have long thought that they are probably created through magnetars, which are highly magnetic young neutron stars. So ages perhaps less than 10 to the 4, a few 10 to the 4 years, magnetic fields greater than 10 to the 14 Gauss. And this at first sight seemed to be sort of spectacularly confirmed early last year by the identification of a fast radio burst from a galactic magnetar, this soft gamma repeater 1935 plus 2154. So you can see here, the bursts from that, which are very much like FRBs, albeit because this is a galactic system, typically of rather lower luminosity. And the interesting thing is that this makes the Milky Way the host galaxy of an FRB. And so what you can ask yourself then is, well, what do the magnetars look like around the star formation? And you can compare the locations of magnetars in the Milky Way with the locations of FRBs in external galaxies, and they seem to match quite well. And so you might start thinking, well, that's great. So, are we really honing in now on FRBs and magnetars? And you might think that sounds very good, but a hot off the press result, which was actually on the archive yesterday, is that there's another now repeating fast radio burst, which is close to M81 and is in fact consistent with a globular cluster in M81. And while globular clusters contain no shortage of neutron stars, they do not typically contain young neutron stars, at least not those which are formed through core collapse, because they don't have any massive stars. And so this may be telling us either that our magnetar models are wrong, or that magnetars formed, for example, by accretion-induced collapse, where you pile on material onto a white dwarf and then crush it down into a neutron star, are also an important contributor to the FRB population.
2 minutes.
Okay, that's fine. I've got one more science slide. So, and then, the network is also working very intensively on both theory and observations of various kinds of transient related to stellar death. And if you're more interested in this, then please do go and have a look at Sylvia Turnan's talk. But two sort of examples, one of which will be talked about later in this session. We're now finally starting to get meaningfully large samples of so-called tidal disruption events, where stars are shredded by supermassive black holes. So you can start to build up their demographics, and you can start to use their details, the events you can really observe in detail, to understand things like black hole masses and spins. And those spins even give you some insight into sort of fundamental physics problems, in the sense that if you have light boson dark matter, it should spin down black holes very quickly. And so you can use the measured spin parameters as a means of actually constraining some of the dark matter. And so all of this work is, based on a wide range of facilities, both computational and observational. There is one major instrumentation update which we should bring you. Some of you will have seen this already, which is that we are now going to be in the process of fully joining CTA, thanks to a large award from NWO, Yakov Venkataramarkov, and a larger collaboration. And so, that is a new opportunity for us to do, very high energy gamma ray astronomy in the coming years. And of course, we also have our ongoing instrumentation program of things which are both active and being developed, although some of those things, for example, Black Gem, unfortunately, is still sitting on Lucia, waiting to be commissioned post-COVID, when we can get back on the mountain. And so I think, we've had a very exciting year for science, despite all the restrictions that have been in place on us. We've made a lot of progress, and we have lots to look forward to in the coming runs of things like EHT, of LIGO, Virgo, and CAGRA. We look forward to JWST and a whole suite of FRB, which are being detected. And of course, we hope that once COVID is resolved, then things like Black Gem and MELICT will start providing us with a stream of more optical transients as well. And so I think, there's plenty to look forward to, both in the coming years and hopefully through this afternoon. And I'll stop there. Thank you very much.
Thank you very much, Andrew, for keeping time also. I will ask the speakers to switch on, to put me on view in their gallery whenever they're speaking, so they see that I make a signal when they have 2 more minutes. Are there questions? I see Yuri applauding, but I don't see any questions. Is there anyone there that wants to make a question? Raise your hand. So what, I may ask, if there is no question, then, can you remind us what is the contribution of the Netherlands to CTA? Is in one of the focal instruments?
It's a good question. I think perhaps I can see that Jaco is on the call, so perhaps I should refer that question to Jaco.
If he can answer very quickly, if not, we can leave it for later.
You're muted, Jaco, or we can't hear you anyway.
No. He's open. He has the microphone.
He's talking, and he's not apparently muted, but we can't hear him.
We cannot hear you, Jaco. Apparently, your
mic. Can you hear me now?
Yes, quickly.
Yes, we can hear you now.
So something is wrong with my webcam if I don't click on it. Yes, so we will contribute to the mass production of the SST camera. So the southern side of CTA will have, well, currently the number is 35, 40 small-sized telescopes which target the highest energy gamma rays. And in Groningen, they will make the focal planes of that. And in Amsterdam, we will do the camera software.
Okay, thank you very much, Jacob. So we have to finish now. The next speaker is Ines, I think. Yes, Inés Pastor Marazuela from the University of Amsterdam. She's talking about chromatic periodic activity in FRB with some number. She's now sharing the screen. For the next speakers, also prepare your screen so that we take the least possible time to switch. And please, Inés, put me on your screen somewhere where you see me. I will switch off my camera, but when you have 2 minutes, I'll switch it on. So we are well on time. So go ahead.
Okay. Hello, everyone. Thank you for having me here today. I'm Inés Pastor Marazuela, and today I'm very happy to share with you the exciting discovery of the chromatic periodic activity in FRB 2018-0916b. So during this talk, I'm going to try to convince you that the activity of FRB 2018-0916b peaks earlier and is narrower at apertive than at LOFAR, ruling out strong binary wind absorption models. So before I go into the detail of our conclusions, I will introduce some of the terms. So first of all, what are FRBs? FRBs, or fast radio bursts, are extragalactic millisecond duration radio transients. They are very energetic, and we still don't know how they originate. So in this plot I show here, that is known as a dynamic spectrum, the intensity of the first detected fast radio burst that we know as the Lorimer burst is shown in a frequency versus time plot. And as you can see, the low frequencies arrive delayed with respect to the higher frequencies. We can quantify this delay with what we know as the dispersion measure, or DM. This delay is due to the propagation of the radio waves through ionized plasma in the interstellar medium. We have models to quantify the expected dispersion measure in a certain direction of the sky from the Milky Way contribution. But what was really surprising about this first fast radio burst is that the Milky Way contribution was only a very small fraction of the total dispersion measure. Yet the additional DM must be thus a contribution from the intergalactic medium, the host galaxy, and also local to the source, putting this FRB at cosmological distances. We currently classify FRBs into observational classes. On one hand, we have the non-repeaters, which are those FRBs that are only seen once. There are more than 100 published FRBs, and they were first discovered in 2007 with this Lorimer burst. The other class of fast radio bursts are the repeaters, which are those FRBs that are seen multiple times. 24 have been published so far, and the first one was discovered in 2016, when repetitions from a fast radio burst first detected in 2012 were seen. Something that was very surprising about the arrival time of these repeated bursts was that it was irregular instead of being periodic as it is for pulsars. But today I'm going to focus on one specific source, FRB 2018-0916b. It is the third known repeating fast radio burst. That's why we know it as R3. And it was found by CHIME, a Canadian radio telescope that observes between 400 and 800 megahertz. The source was later localized to a spiral galaxy located at 149 megaparsecs. It is the second repeating source to be localized, and this was actually a result from some of our Network 3 colleagues. But the most striking property about this source is that it was found to be periodically active every 16.3 days. This means that for 5 days, the source is active and emits bursts at irregular times, and then it becomes quiescent for 11 days before becoming active again. This property was really surprising because it had never been observed in an FRB before. So the FRB community started proposing new models that could give an explanation to this periodic phenomenon. And we can distinguish two main types of models. On one hand, we have the binary models, in which the fast radio burst source, a neutron star, is located in a binary system with a companion that can be either another neutron star or a main sequence star. This companion emits winds that shield the emission from the fast radio burst through free absorption. This means that we are only able to see the emission at the moment of the orbit when the fast radio burst is facing Earth. The other type of models trying to give an explanation to this periodicity are the isolated neutron star models. In this case, the periodicity could be either due to the precession of the beam of the isolated neutron star or to an ultra-long period magnetar that rotates with this 16.3-day period. But when these models were proposed, there were not enough observations to check if the predictions that these models made were correct. So with the Apertif team, we decided to start a follow-up campaign on this source using 2 radio telescopes located in the Netherlands at different frequencies. The one observing at high frequencies, Apertif, uses the ARTS backend to look for fast radio bursts, and ARTS is funded by the Network 3. So what we consider high frequencies here is 1370 megahertz. And we used Apertif to spend almost 400 hours on source. The other radio telescope we used is LOFAR that observes at low frequencies at 150 megahertz. And we spend around 50 hours on source, but all of them scheduled at the predicted active days. LOFAR had been used in previous occasions to look for fast radio bursts, either through blind searches or to follow up non-repeating sources. But so far, all observations had been unsuccessful at detecting. I'm going to give you some more information about the kind of science that we do within the Apertif FRB survey. We have 2 main science goals. One of them is to follow up non-repeaters. For instance, the work presented in Ostrom et al. Follows up the first and the second repeater and shows 30 detections of FRB 121102. We also focus on looking for new, previously unknown non-repeaters. One example of this work is presented in Connor et al. 2020, where we show the properties of a bright, high rotation measure fast radio burst that pierces the M33 halo. And we are currently working in the ARTS survey overview and data release of Apertif FRBs. But now moving back to our source, R3. In these observations we took with LOFAR, we detected R3 not once, but 9 times. These are the first detections of an FRB below 200 megahertz ever, proving thus that there are indeed FRBs at low frequencies. Additionally, we found 54 bursts with Apertif, and this is the second largest data set of bursts after chimes. None of the detections took place simultaneously at both frequency bands, as you can see in this plot. And I will also bring to your attention the arrival phase of the bursts. I will come back later to this point. So here is the arrival time of each of our detections with the signal to noise ratio of the bursts and the modified Julian day. The dates spanning this plot are between March 2020 and December 2020. So we started when the pandemic was already here. The LOFAR bursts are shown in dark red, and the Apertif bursts are detected in light green, as you can see here. And I'm also showing other detections by other instruments for comparison. What we see is that all of the bursts fall within the expected active days represented by these gray shaded regions. But we see that the Apertif bursts, most of them seem to arrive before the activity peak day at chimes frequencies, whereas the LOFAR bursts arrive after this activity peak day. So here are the 9 LOFAR bursts we detected. We see emission down to 120 megahertz. And apart from that, the bursts are quite featureless. They don't show complex time and frequency structure. What they do show is a scattering tail, as seen in this exponential decay in the intensity of the bursts. The scattering timescale is 45 milliseconds, and this is consistent with the contribution we expect from the Milky Way. This tells us that there is no significant contribution to the scattering local to the source. Both the presence of emission down to such low frequencies and the lack of significant contribution to the scattering tell us that the source lives in a clean environment that, for example, doesn't seem to be compatible with a supernova remnant. In contrast, the apertive bursts, most of them show very complex time and frequency structures. Here, there are 6 out of these 54 bursts. Most of them show a single component, but we do see bursts with 2 components, 3 components, 5 components, and we even saw a burst with 12 components, which is quite surprising. The bursts with multiple components show this typical downward drifting frequency that is typical in repeating fast radio bursts. But when we look at the arrival phase within the 16.3-day period of the fast radio burst, we see that the apertive bursts, represented here in green, arrive earlier in phase and for a shorter amount of time than the time bursts that observes at intermediate frequencies. And the low-far bursts in red are even more delayed in phase. This means that the activity of FRB 2018-0916b peaks earlier and is narrower at higher frequencies than at lower frequencies. This is actually the opposite to binary wind models predictions, because the free absorption should allow high-frequency bursts to escape for a longer amount of time. And this brings to my conclusion. We have seen that the activity window of R3 at higher frequencies is narrower and peaks earlier. This, together with the presence of emission below 200 megahertz, strongly disfavors binary models with companion winds. We have, from the polarization information we had for some of the apertive bursts, we see that the polarization angle remains flat within individual bursts, and we have ruled out any potential aliasing. This is in conflict with precessing magnetar models. So the current picture we have of R3 is that it could be either a neutron star in a more complex binary scenario than what has been proposed so far, or that it is an ultra-long period magnetar. All of this work is presented in this paper that has been very recently accepted in Nature. So I wanted to thank the arts and the apertive teams that made it possible, and also thank you for listening.
Thank you very much. People can applaud with signs, not with real applauses. Very nice talk, Ines, very professional and well presented. Thank you very much. Are there questions from the audience? Do you want to raise your hand if you do? I have a question, but I don't want to be the only one asking questions. Natalie, please. Natalie?
Hi, Ines, thank you for the great talk. Is it possible to say something very general about the population of FRBs based on your results? Like probably it's a homogeneous, heterogeneous population. Like, can you make some kind of prediction of how many of the FRBs, like what percentage, are likely caused by magnetars?
So I think that currently, at least the repeating fast radio bursts are very likely produced by magnetars. There are still other theories that haven't been ruled out, but I think that in general, the community agrees that the magnetar is the most likely progenitor. But then if all of them show a periodicity or not, I don't know if that's also part of your question. That's not certain yet because, well, this periodicity has been observed in this source, but also the first known repeater also seems to show a periodic behavior. So there seems to be something in common, at least between these two fast radio bursts. Does that answer your question?
Yes, thank you very much.
Okay, Jaco, if it's very short only, and Ines, you have to answer very short.
Okay.
Yes, you talked about there's no supernova remnant present, but I guess that depends on how big the supernova remnant is and how much ionization is there, right?
Yeah, of course. But I think that if it was a young magnetar, the supernova resonance should be denser, and we should see some kind of signature in this scattering, or also maybe the low frequency emission would be blocked by free absorption.
But even that depends on the
Sorry,
environment.
Jaco, I need to interrupt you. It's time for the next speaker, and I have been asked to be extremely strict. So please talk to her in private. I think it's a very interesting discussion. Thank you very much, Ines. The next speaker is Sjoerd van Velzen. Sjoerd, please, can you share your screen? His talk is about the first population analysis of the tidal disruption events. You can start, please. Please put me in camera so that you see me the indication of 2 minutes. Probably you need to switch on your mic if you're speaking, because we don't hear anything.
Hello.
Oh, no.
Okay.
Yes, go ahead.
Hi. Yes, thank you for and thanks for inviting me or for accepting my contribution here for this talk. And so this talk is about stellar tidal disruption events. I will explain what they are, why we care about them, and then what we don't understand, and then some very recent progress that we were able to make thanks to a larger sample size that was also already highlighted by Andrew earlier today. So let's get started. This is NOVA Network 3 brought together here. So we care about fundamental questions, and often fundamental questions about compact objects. So what are some questions you may have in mind? Are black holes spinning? That's very hard to measure, but a very fundamental property we want to measure of black holes. And is accretion physics scale invariant is another really fun question, I think, because it connects accreting white dwarfs to supermassive black holes. And it's something that is very elegant. And then the last big scientific question that is often on my mind is the origin of massive black holes that occupy the centers of galaxies. We don't know where they came from, how they formed in the early universe. So from all of these questions, some progress, of course, has been made. They're decades old, but it's nice to approach this from a new angle. And that's where stellar tidal disruption events come in. So here you see a snapshot from a simulation pasted over an artist impression of a galaxy. And to really finish my introduction, I will just show this movie. So sit back and relax. It's 40 seconds long. Here is a star. Passes the black hole. Now it's disrupted into streams. Some of this gas can accrete. You can make an outflow. And finally, you can take an event horizon telescope image. So of course, this is a Hollywood rendering of what happens, but this is really based on the on real GRMHD simulations and our physical understanding. And so basically, what you have a quiescent black hole that is very hard to measure with any observational methods. Then a star comes by, a lot of energy is released, and now we can really study this system. So let's go back to these fundamental questions from the start of the talk. Are black holes spinning? So it turns out we can measure this if we measure TDE, the rate of TDEs from high mass black holes. X-ray observations, of course, is another way, but TDEs from high mass black holes skim the horizon, and so their rate becomes sensitive to whether or not the black hole is spinning. Then a question of scale invariance of accretion is really nicely addressed with radio observations of TDEs, tidal disruption events. And finally, the question of black hole genesis turns out to boil down to measuring the rate of tidal disruption events in low mass galaxies, and then we can discriminate different models for black hole formation. So this is to motivate you to listen to the rest of the talk, which is trying to explain what we know about these events. And here is a little spectral energy distribution of a galaxy that is hosting a tidal disruption event at 2 wavelengths, we see X-ray, and optical is elevated with respect to the archival observations, which are shown in gray. And then in black, you see the new transient emission. So if you see this with your telescope, you measure a black body in the X-ray and infer a typical radius, and that is of order the Schwarzschild radius. Whereas if you measure the optical emission, it's more like a few 10 to the 4 Kelvin, which corresponds to 1,000 gravitational radii. So 2 different emission sites that we see in this event. And the X-ray emission is certainly coming from the debris that's being accreted, but the origin of the optical emission is unknown. So that concludes the introduction. Tidal disruption events are very powerful tools, but we don't know where the optical emission is coming from. So that is clearly something we want to address, and that will be the focus for the rest of this talk. And just a brief advertisement for the rest of the SED. Of course, there's radio emission, and you can study just jet disk coupling. There's also dust reprocessing that you can see in the infrared. So I've also worked on these topics, but I won't be focusing on this here. Just reach out to me in Slack or anywhere, and we can talk about those things. But what about the optical emission? So this is really where most of the tidal disruption events are found. Here on the left, you see a cumulative distribution of events. So the number is increasing as a function of time, starting in the late 90s. And then here in the green, which is all the optically selected sources, there's a little spike. And we go from 30 to almost 60 in a few years, which is the start of ZTF, this Wiki Transient facility. And really the trick of ZTF is to just put a really big camera in the primary focus of the telescope. So you get a humongously large field of view, as shown here on the right, compared to other telescopes, other cameras. And you have a 47 square degree field of view. So you can see a lot of the sky. ZTF takes images of the sky every night. And then we look for transients. So we look for optical tidal disruption events. I have one slide on how we do this. And this is to show you that even though you have a large area of the sky, it's not really easy to find tidal disruption events, because you have to also deal with supernova and AGN flare. Both, of course, are also interesting, but not the topic of this talk. And fortunately, tidal disruption events have a constant color. And you can see them here as the purple points, purple diamonds. And then supernova, because there are explosions, their color increases with time, they're cooling. So they're all up here. So then the trick is to make this selection, take spectra and UV follow-up observations of as many sources as you can. And then we arrive at 17 tidal disruption events that we found in ZTF. That was the population paper that was released over a year ago. And we all named them after Game of Thrones characters, just to keep track of all of their names, and because it's fun. And one really important result, so now the rest of this talk is about that paper. One important result is that we can establish a spectroscopic classification scheme for these sources, right? But that's what we always do in astronomy. If we don't understand something, we first try to characterize it and then look for physical explanations of this structure in our data. And this is building on earlier work, also work by Nadia, who we will hear later in the session. And so we have 3 classes of TDEs. We have TDEs with only hydrogen, tidal disruption events with hydrogen and helium, and tidal disruption events with only helium in their spectrum. We don't know why these different spectra show up, right? Because we don't know the origin of optical emission of TDEs. And so maybe you think this classification is arbitrary, maybe there is a continuous distribution, but then something really beautiful shows up if you plot the black body radius and temperature of these sources. And now we see a very clean separation of all the sources with hydrogen and helium in their spectra and all the sources with hydrogen only, right? So green and red, or circles and squares if you're colorblind, they separate really cleanly in black body radius. And also all events have a similar total luminosity. So this dotted line here is simply the black body luminosity. And that means that dusk reddening is not very important. Then these small photospheres are really the most common in our sample. So here, this is the rate as a function of radius. So the small black body radii are an order of magnitude more common in a volumetric sense. And perhaps we can explain this with the disruption of lower mass stars, which yield lower photospheres and therefore higher rates because lower mass stars are more common. So that's already one really key population property, right? Even though these hydrogen and helium TDEs occur at the same observed rate in your sample, the ones with hydrogen and helium and also Bowen fluorescent lines are much more common. Okay, then one important correlation that is also seen in the data, continuing with the population study here, that if you measure the black hole mass from the M sigma relation, which may or may not hold at these low masses. So that's what I'm showing here on the x-axis. This is the estimate of the black hole mass. And here is the time scale of the decay rate of the light curve. And there is a correlation with some scatter that is actually similar to the scatter in the M sigma relation itself. So bigger black holes have longer decay timescales. And that makes sense because the fallback rate of the stellar debris is also longer and increases with the root of the black hole mass. So that looks encouraging. We have some structure here in the data. But then there is also a non-detection. And you think like, why are you showing a non-detection? You only have 1 minute left. But this is really important non-detection because this is between the rise time and the fallback time, just measured from the light curves. And there is no correlation between these two properties. This means that there are two time scales in the problem. Otherwise, the rise and fallback time, fall time would be correlated. And since the decay of the light curve can be explained by fallback, the rise time must be explained by something else. And that brings me to the summary here. Here is real data of a real tidal disruption events, multiple bands on a log scale. And we have the increase is really set by photon diffusion. That is the new insight that we gained here. Photon diffusion is proportional to the density in the photosphere. Then the decrease in the light curve is set by the fallback rate of the debris. And then finally at late time, we see the accretion disk. And what's next? We've seen tidal disruption events coincident with neutrinos. That's a different talk. Will be more radio follow-up, infrared observations with James Webb, Irisida Black Gem, and of course the Rubin Observatory, for which I'm the coordinator of the TDE group. So reach out to me if you're interested. The data of the Rubin Observatory will be publicly alert data, so we can all work on this. And of course, Black Gem we'll hear about next. And that's it. Thanks.
Thank you very much. Sure, there are two questions, but I think I can only go to one. The first one is Zsolt Parazi, so you can ask first, and let's see how it goes.
Hi, sure. Nice talk. Can you please tell me what fraction of these TD are detected in the radio? And also, I'm quite interested, what do you think, what fraction of the TD do you miss because of dust obscuration? So infrared observations could reveal more.
Yeah, so about 1 in 3 are detected in the radio, and they are lower redshifts. So maybe all of them can be detected if we have infinite sensitivity. And then the fraction of TDs that is obscured by dust is unknown, but I'm looking into this right now by searching for their echoes. And then if we see only the echo in the infrared, then we can infer that something happened in the black hole. So yeah, stay tuned.
Okay, thank you very much. Phil, you have time. 1 minute question and answer.
Yeah, okay, thanks. Yes, actually, kind of a related question is the X-ray selected sample. Do you have enough of them to see if there's any difference between the X-ray selected sources and the optical ones from the ZTF? There has been some investigation about this, and there's a recent paper by Mummery
a student from Oxford, and he finds a difference between the X-ray selected ones and the optical ones. But then others studies did not see this, and the difference, the predicted difference is in the black hole mass, but measuring the black hole mass is difficult. So I think it's still up for grabs right now, but it's really a good way forward. And yeah, in general, some predictions say that there should be no X-rays from the lowest mass black holes because they're all obscured by this super Eddington outflow, because you get the super Eddington luminosities. And that's maybe seen in the data, which is like both good and bad news, because it makes sense, but it means less X-ray selected sources from intermediate mass black holes.
Okay, thanks.
Okay, thank you, Short, and thank you all for keeping time. So I ask, stop sharing your screen. Thank you. And Anna Yuranova, can you share your screen? She's going to talk about AGN outflows probed by spectral timing techniques. I find it very useful from Shur that he was looking at me, and when I made the signal of 2 minutes, he responded with the 2 minutes fingers again. So I know that he saw me, otherwise I have to interrupt. So Anna, if you see me, put me on top on your list and keep an eye. So please go ahead.
Thank you. Hi, everyone. Thank you for the opportunity to talk here. Before I start talking about the spectral timing applied to AGN outflows themselves, let me just introduce the Fourier timing techniques and their benefit in being used for AGN observations in the X-ray band. What you're looking at here is a small cartoon of the central regions of an AGN. We see a black hole surrounded by an X-ray emitting accretion disk, and then another X-ray source, an X-ray corona, which is located somewhere close above the accretion disk. So what I was trying to illustrate here is that part of the coronal emission doesn't leave the system immediately, but it first illuminates the accretion disk, and then the reprocessed emission is re-emitted and can be secretly observed by examining Newton these days. So if we could isolate these components that are resulting from this process, we would see this direct parallel emission and then some kind of a reflection spectrum. I couldn't stress more that this is nowhere near the actual shape of the reflection spectrum, but I hope it will be enough to illustrate the point. What I hope you can also notice here is that the photons coming from the X-ray corona will need some time to reach the accretion disk. And so if the coronal flux is variable, what we would see would be that the reflected spectrum would be delayed with respect to the direct emission. Now, if we could then isolate the light curves coming from different energy bands affected by these two emission components and compare them, we wouldn't be able to get the time lag from this directly. It is basically for two reasons. The lag is typically very short, and also it is normally detected only in certain time scales, temporal frequencies. But this is where the Fourier timing techniques become very important, because they can basically overcome both of these problems. Since from the definition, they act in the Fourier space instead of the timing, instead of the time domain. And also they focus on the statistical properties of the variable signal and not the actual realization of the light curves. So using these Fourier timing techniques, these lags associated with the light travel time have been observed in quite a few AGNs already. And since we know that these lags are connected to the geometry of the system, we can use them to map the innermost regions of AGN. But now let's focus on the ionized outflows. So if this system also contains some outflowing gas, that can respond in its ionization state to the coronal variations, it has been shown that additional time lags can be produced from these delays. As you can see here, this was simulated for a low ionization absorber, which could be observed with XMM Newton RGS. And so we have here a transmission spectrum of the absorber. And what you can see is that there are lags produced over the whole range of energies, but at certain energies, you can really connect the absorption features to the lags. And so we see that the lags really leave some characteristic pattern in the lag energy spectrum. Now this is actually possible only for low ionization outflows because of the energy resolution and effective area of current instruments. But looking ahead to Athena, the future of the X-ray observations is quite bright. If we just briefly compare the Athena spectral resolution, or more importantly, the resolution of the cryogenic X-ray spectrometer on board, and then to the instruments on XMM Newton, we see that there will be quite some dramatic improvement also in effective area and the time resolution, which are all qualities are very important in doing timing studies. So the question that immediately arises is, what will Athena see in terms of timing of AGN outflows? And even more importantly, can we use the timing properties to characterize these objects? So to address these questions, we carried out simulations for Athena XIFU. And namely, we simulated a highly variable narrow line CFET1 with an ionized outflow that is intervening the line of sight, and so is observed in absorption. To outline the basic idea behind this, the ionization parameter, which characterizes the ionization state of the outflow, will be in equilibrium proportional to the ionizing luminosity. Specifically, this relation is also tied by the gas density and its distance to the ionizing source. So if we now look at a piece of light curve, which is quite variable, so this light curve represents the variations in the continuum flux. And then we see how the relative concentrations of individual ions evolve as a function of time. Then for nearly equilibrium conditions, you can see that the variations are very strong and also quick enough so that we cannot see or detect any delay. The concentrations are, in this case, set by this relation. Now, if we change the parameters of the outflow, we increase distance to the ionizing source, or in other words, we decrease density, which is tied with this relation. We see that the response is delayed and also smoothed. Going even further away, we can see that this delay is increasing and the smoothness does as well, out to a certain point where the concentrations become essentially constant and the overall ionization state is set by the average AGN flux. Looking at the spectrum as a whole, you can see that for the highly variable case, the changes in the spectra can be quite dramatic. See, we have a low ionization state and high ionization state. We see that most of the lines disappear. But how does this translate into the timing properties? Here we are looking at the time lags, which you already know, and also coherence. Just to make sure it is clear what we're talking about, the coherence is a measure of linear relation between light curves that we are comparing. We're comparing an unabsorbed light curve to a light curve extracted from the visualized energy bands. And so if these two light curves are linearly correlated, then the coherence will be equal to 1. And of course, the less this applies, the lower will be the coherence. The lowered coherence that we can see that is associated with the absorption features so affects the time lags, because when the coherence is low, these time lags that are detected this way cannot be simply interpreted as the actual delays in the signal. And so this is all due to the nonlinear gas response. If we do the same trick as before, so we add outflows located further away from the ionizing source, we see that this pattern that the absorber leaves in the coherence spectra, and also the time lags, changes quite strongly as a function of the outflow distance. So this brings us back to the second question I mentioned at the beginning, and that is, we can use the coherence spectra or generally the timing properties to constrain the outflow parameters. And to address this question, we performed a fit of the simulated data with a set of models or modeled coherence for different distances. And what you can see here is the result, the reduced chi-square, and what is quite clear from this figure is that the best fitting model is significantly different from others at different distances. So from this, we can actually conclude that by modeling the coherence spectra and comparing it to the observations, we can actually constrain the outflow distance and density, which are parameters that are very important in estimating the role of the outflow in the context of AGN feedback. Now let me summarize the talk. So what we've seen is that Athena XIFU will allow very detailed insight into spectral timing properties of ionized outflows. If we see that these absorbers are actually reacting to changes in the X-ray radiation, then we would see that this response is highly nonlinear, which in turn produces complex behavior of time lags. The good thing about this is that the coherence itself, the coherence spectra, could be used to provide constraints on the outflow properties and consequently also the role of these outflows in AGN feedback. Okay, thank you for your attention. And well, I think we have time for questions, so if you have any.
Thank you for chairing the session, Anna. We do have time for questions. Yes, that's okay. No, but thank you for a very nice talk, very clear and well presented. All the speakers so far. Thank you very much to all for keeping time and being so clear. Are there questions from the audience? I have a question. So you say you show this delay as a function of the distance between the ionizing source and the absorber and also the smearing. I presume that the increase in the delay is just light travel time. What is the smearing? Is because the region is extended or and then connected to that is, do you assume that is the ionization instantaneous?
Yes, so this is actually the point. So the delays are not really related to the time, light travel time, but I probably could have stressed this more. It is more related to the recombination time scale of the gas itself. So it would be probably more natural to talk in terms of the density, because the recombination time scale is related to, like, inversely proportional to the gas density. But since we can use this relation, you can also talk in terms of the distance, which is probably more interesting, since that's what we are interested in, because we'd like to know where these outflows are actually located. So.
Okay, thank you very much. Sorry if I misunderstood that part, but I think it was clarifying. Thank you very much. Is there any other question? We are on time now, so no, I don't see any. The next speaker is Valentina Peirano Bastias. She's my PhD, so I asked Yuri to take over this last talk as a chairperson, and also he is the chair of the next one. So I will.
So I'll mute you now.
Yes, please.
Hey everyone.
Thank you. Yes.
Hey Valentina, thanks for preparing a talk. Give me 1 minute to get started and then you can share your slides. Okay. One final talk before the break by Valentina Peirano. Then we have a 15-minute break and then a second half. So if you have a question, the first student who asks a question, I'll personally send them a bottle of wine or non-alcoholic beverage of choice, as I do every NAC. So I see 100 participants. I want to see some questions at the end of the next 12 minutes.
The talk.
And if you ask yourself a question, I will think about it. You can also post your questions on Slack or in the chat, and I'll try and keep an eye on it. Valentina, whenever you're ready, go ahead. I'll give you a warning after about 12 minutes. If you share your screen, we're good to go.
Oh, you can see my screen now? Yes. So, hi, my name is Valentina. I'm a PhD student with Mariana, as you said, in the Kaplan Institute, University of Groningen. Today I'm going to talk about a project that hopefully will be soon published and you will be able to read about the relationship between time lags and luminosity in neutron star low mass extra-binary. So, well, the previous speaker really did like some kind of introduction into timing. So maybe I won't go into this in so much detail anymore, but I still wanted to give a little bit of an introduction about what is timing analysis, what are kilohertz QPOs, and how we study them. So when we observe one of these sources, this is basically what we see. This is a light curve, so it's rate versus time. And we see that it's very variable. And some of the variability is due to noise of different nature, but also we see what we call quasi-periodic oscillations. And we call them like that because they're not really periodic, but they're almost periodic, basically. And we cannot really study them in detail, just looking at them in a light curve. So what we do is taking them to the frequency domain in a power spectrum, doing a Fourier transform, and we look at it here. And QPOs appear in a power spectra in peaks like this one. And we can fit these peaks with a Lorentzian function, for example, and we can use the parameters of the Lorentzian to characterize the QPO and study and compare them to QPOs in other sources and all these things. We focus mainly in the higher frequency end of the power spectrum where the kilohertz QPOs are, and they call like that because they are at kilohertz frequencies. Usually, kilohertz QPOs come in pairs. So we have always a lower, not always, but we have a lower and upper kilohertz QPO, and that depends purely on the frequency at which they present themselves. Sometimes they're also alone. And we study them because we believe that they're originated in the innermost part of the regions of the low mass extra-binary, very, very close to the central object here. This area is very interesting because we want to understand what is happening with the matter that is falling into the neutron star or the black hole, but also what type of processes are happening to the emission that is coming from these areas that we see this variability in the emission of a low mass extra-binary. So we can use this type of, we can use the power spectrum to study QPOs, but we can also take it a little bit further and use the cross spectrum and other high order timing products to study them. But for example, the lag, that is exactly what the previous speaker was talking about. So a cross spectrum works basically as like a power spectrum, but in this case, it allows us to understand the cross correlation between two different light curves. So I don't really use two different light curves. I use the same observation, but I divide them into energy bands and I compare them to each other. Usually one band is like low energy or called soft band, and the other one is higher energy or hard band. So we compare them to each other, and the time or phase lag comes out as a product of this process and basically reflects the time delay of the variability of one of the bands with respect to the other. So for example, if I say that we can observe a hard lag, what I mean is that the variability of the hard band is lagging behind the variability of the soft lag, arriving later to the detector basically. And the opposite happens if I say that it's a soft lag. So the variability of the soft band is lagging behind the variability of the hard band. So with all these tools, we can actually analyze our data and analyze the QPOs and try to discover like why are they there, why we can observe them. So what we did is select data from the literature, basically from this paper of Troyer et al. 2018, where they study the kilohertz QPOs of 14 different neutron low mass extra binaries. And this figure over here is like one that they have in the paper. It's slightly changed, but it's basically the same. They have here the time lag versus energy. Time lag here is average over all frequencies, overall QPO frequencies. And what they did was fit the data with the linear function, which is this red line here. And what we did was organize them in a way that you can see the effect that I'm going to show you right now. So if you look down and to the right, you'll see that this red line becomes flatter and flatter somehow. So we found this like very interesting that was happening with these sources. And it also happens if you look at their data also, the RMS amplitude versus energy. It's not that evident here as it is in the lab, but still we fitted here a broken line model. And if you look at the slope below the break, it also seems at least slightly getting flatter as you go down and to the right. So we think that there must be some property of each one of the sources that is making the variability change in this way. And we need to find a quantity that will allow us to represent this change between different sources. And we think that this quantity could be the luminosity. So this comes from a paper of Mariano of 2006, where he compared the Q factor, which is the with a maximum of the QPO divided the frequency of the QPO and the RMS amplitude versus the luminosity. And he found some relations between them. This, you will notice here where it says L, because this corresponds to the lower kilohertz QPO. And it also has a max because this actually comes from his data where like he has like the Q versus frequency and the RMS versus frequency, and this is the maximum value in these plots basically. So so what he found is that Q max increases and then decreases with luminosity, and the RMS like remains constant up to a certain point and then decreases also with luminosity. So here we see that there is like the luminosity or whatever luminosity is representing in this case has some effect in the variability of the source. So what we did was select 8 of the 14 sources that Troyer et al. Worked with. And we selected these 8 because we know that these 8 have a better coverage in the QPO frequency than the other 6. So you see here, like all the sources like have like a more better, what I said, better coverage in the QPO frequency than the others. So we selected these sources and we compare the lag to the luminosity, and we find this. This is the slope of the lag spectrum versus the luminosity. When I say slope of the lag spectrum, I basically mean the slope of this fit that is here in the figure that I showed before. And when we compare it to the luminosity, we see that it decreases exponentially with increasing luminosity. And we see the same with the RMS, with the total RMS amplitude. Total RMS amplitude also decreases exponentially with luminosity, which is very, very interesting. And if both quantities behave so similarly against luminosity, it will only make sense to compare them to each other. And we see that they actually are very strongly correlated to each other in this, like in a linear way. So we think that this type of result suggests that there is one single property of the system that is driving the changes that we observe in the variability of them. But like, how will we describe this type of system in a more realistic way or more physical way? How will the model that describes this idea will look? So we think that it will look like this. This is a very simple sketch of how it will look like, but here basically we have the compact object, in my case a neutron star, surrounded by a disk and by a corona. The Comptonizing medium that will interact with the light coming from the disk. And what we can observe from a model like this could look in different ways. First, we could have a direct emission coming from the disk. That is a soft photons emission. We can also have like the disk reflecting off the corona and emitting again in higher energies. And we will observe a hard lag because this is arriving later to our detector, as like the previous talk said before me. And we also could have like the emission reflected of the corona could go back to the disk and then get emitted towards us again with lower energies, and we will see a soft lag. And soft lag is exactly what we see in the data that I showed before. These all are like soft lag, which is nice because it means that our model somehow like is compatible with what we observed in the data. And what we think is happening is that both the disk and the corona are in some kind of coupled oscillation. And when we observe this maximum strength and variability, we have them both in some kind of resonance with each other, where like they maximize each other oscillation. But when the luminosity increases, something happens with the corona. It becomes less, the contribution of the corona to the total emission of the system becomes less important, and they're not in resonance anymore. And we observe this decay of like the strength of the variability in the source. So this next slide is like a summary. So to like reach conclusions with everything that I explained. So here I have like the main results. We know that the slope of the lag decreases exponentially with the luminosity. We know that the RMS amplitude also does the same. And because of the results of Mariano 2006, yes, we know that also the Q max and the RMS max that he defined also depends on luminosity, and they also decayed like from certain luminosity decay with it. And we think that this is due of like a couple oscillation mode between the corona and the disk. So when the luminosity increases, the corona contribution becomes less important because of changes in its properties. It could be the size, the temperature, the optical depth, for example, and the feedback fraction of photons that go back to the disk after being reflected of the corona decreases. So the lag and other QPO properties become less significant because the disk and the corona are not in resonance anymore. Okay, that's it. Thank you.
Thank you, Valentina. So I see some interesting discussion going on the Slack about previous talks. If people have a question for this talk, please raise your hand. If you're a student, tell me you're a student and I will send you a bottle of wine or Coke or whatever you want. Coca-Cola, I mean. So I'll give everyone a minute. In the meantime, I'll start with Phil. Phil, you want to ask your question?
Yeah, thanks. I don't need the bottle of wine, I think. Well, if you want, but and thanks very much, Valentina. That was really nice, nice talk. And what I was wondering was, in you used a sample of several sources, so presumably this correlation is global across them. But what about within a source? Because then you have the frequency dependent changes as well. So I was wondering, is that all just coupled to the luminosity, or is there an extra axis with the QPO frequency in, when you're looking at a single source?
Yeah, I mean, there's also links like among one source, so you also see these type of changes. But in this case, we're like really analyzing the source. Well, we're not really assuming that like the sources always has the same luminosity and the same everything now, because for example, you see the error bar in the luminosity, we're really like expecting some span in luminosity for the source. But in this case, we really compare them like separately, like the average of luminosity of each source and how the changes compare to that. Does that make sense? I'm not sure how this will happen in within a single source.
Okay, thanks.
So Valentina, from the set in Troyer, you there were 6 you didn't use. Huh?
Yes.
Is there? Do you think that somehow introduces some kind of selection effect? Are these 6 random, you think, or are you unselecting less active, dimmer, otherwise different sources?
Yeah, I mean that's a probability. Like always, it's always a probability that when we make any type of study and we select the sources that have better sampling or we have more observations on them, usually it's because they're more bright or because I don't know the QPOs are more like strong and all these things. Really, yeah, they could be affecting. But also, if we had included them, we would be affecting our results as well, because really much of the things that we measure depend on the frequency of the QPO as field, as you said. So if there is not enough sampling along the entire frequency that the QPOs appear, we don't see the entire behavior of the QPO in that particular source. So yeah, true that if we select only these 8 that are better observed, we are making a selection in that way, but also if we include all of them, we're affecting our results in a completely different way as well.
So is there observationally a way out of that? If we redo this a few years from now, will it be better, or is it intrinsic?
I hope it will be better. If if it's everything, like observations get better and we can observe these sources and be able to detect them in more stages in their evolution, then yeah, I would think it will get better.
Thanks very much, Valentina. I'm looking at the other screen and I see we have okay, so there's one question on Slack, Valentina, that Picky Atri asks. I'll refer you to answering it over there because we've hit the time for the break.
Okay.
So if people who haven't signed up for the Slack channel yet, please do that and continue the discussion there. Thanks everyone for looking to the first 5 talks of this session. Thanks Mariano for chairing the first half. We take a 15-minute break now and we start again at 4 Dutch time with the second half of this session.
Thank you, Yuri. And you did a good job here, and everyone did. The speakers were actually very good, very impressive talks before. So sorry, I cannot stay for the second half. I have another meeting.
All right, we will, bye Mariano, we'll leave this stream running and I'll see you back here at 4. Well caffeinated. Paul, you want to get your video and slides ready in a bit?
It should have been sharing already, Yuri. You were not seeing it?
Maybe I have too many screens. Oh, sorry. Yeah, you probably were. You were hidden behind my other screen. Yeah, looks good, Paul. My apologies for the confusion.
Hi, Paul. Can you hear me?
Yeah, we can hear you fine. And it's 4 o'clock, so it's time to get started again with the second half of this afternoon session of the Netherlands, the Royal Netherlands Astronomical Society yearly meeting NAC with the afternoon on Network 3. And starting off in this last part of this afternoon is Paul Groot. We have 5 great talks in 15-minute slots each. So let's do 12 minutes talks plus some time for questions and a handover. There's some discussion going on Slack, so join in there if you will. Ask your questions in the chat here if you want me to ask it, or otherwise raise your hand and do it yourself at the end of Paul's talk. Paul, if you're ready to go, then please take it away.
Yeah, thank you, Yuri. So thank you for the chance to update you on Meerlicht, both the status as well as the science results. You can see the telescope here on the right in the dome in Sutherland in South Africa. And on the left, we show a beautiful picture of the Orion Nebula that, of course, you recognized. And this is coming straight out of our sky survey. Normal data, nothing special. It's beautiful to see because the faintest stars in this image will be about 20 this magnitude. And that brightest star, which is Iota Orionis, is 3rd magnitude. So you see that even though it's highly overexposed, it's not throwing its light everywhere, which is a testimony to the fantastic optical quality of these telescopes that were built by the NOVA Optical Infrared Group. Let me remind you what Meerlicht as well as Black Gem, what kind of telescopes they are, because they are 99% identical. So it's a design where we have the main mirror here at the back of this carbon fiber mirror cell, secondary mirror where we actually do the focusing and which is on the tip-tail stage, so we can also guide with that. And then the light goes through 3 lenses to enter on this big chip here at the back. A 10K by 10K CCD that images 2.7 square degrees on the sky at a resolution of about half an arcsecond per pixel. The system is a fast readout system. It has an atmospheric dispersion corrector in this lens barrel here. So the 3rd lens actually can move sideways to act as an ADC, which also allows us to get great optical quality in the bluer bands, in the U band, which are generally not available from other wide field imagers, even though those are fantastic in their own right. It's all robotic, and that of course came into the real advantage at the start of the COVID-19 pandemic, because Meerlicht was already operational then, and it has been throughout the whole pandemic period. Here's another view of this big chip. These are the biggest CCDs that you can get, 10,000 by 10,000 pixels. Beautiful quantum efficiency, especially in the blue. And we couple it with 6 filters. So the well-known Sloan set, UGRI-Z, but we optimize them so that these are very steep edges and basically no overlap between the filters. And we added to that a broader band Q-band filter that runs from 440 to 720 nanometers. And here on the right, you see the filter wheel, and this turns around in just a few seconds. So we actually can get 6 filter data if we want, but always multicolor filter data. And I think that is going to be a big development also in the future, and also with other wide field imagers to really make advantage of these multicolor observations. Sjoerd already showed us a nice example of how you can distinguish TDEs from supernovae and other phenomena, and you need this multicolor information for that. I was saying that blackjam and Meerlicht are 99% identical, so let me just briefly spend one slide on blackjam. As Andrew was already saying at the introduction this afternoon, they are installed in on La Silla in Chile. So here you see those 3 mushrooms. Those are the blackjam domes. Here you see one of the 3 telescopes during the installation in one of those domes. And here you see them on the right, you see them from the sky. Nice drone footage taken by ESO for us, where we were installing the 3rd dome. The telescopes are installed, but of course we had to leave La Silla at the end of March last year, and we have not been able to go back. Just before we left, we actually took first light, technical light on all the 3 telescopes, and that looked beautiful. So without, you know, specific special pointing, no guiding, not even aligned properly to the pole, we already got 1.3 arc seconds in the first technical light image. And in 10 seconds of integrations, we already went to 20th magnitude with a signal to noise ratio of 5. So both are really very close. Well, the second one actually is on spec. The first one, we will get there with some guiding and better alignment. We will, of course, go back to Chile as soon as we can, but well, we all know that international travel currently is prohibited, certainly to South America. To be continued, blackjam. Meerlicht, the telescope has been going strong throughout the pandemic. So it's now 15 months since the lockdown started, and since basically anyone has been at the telescope. There's been one servicing where they cleaned the mirrors, but other than that, the telescope is functioning very well, and this is also due to how well it was built. We now have more than 100,000 science frames taken, specifically over 2019, 2020, now 2021. So the real data taking is the number of observations per month versus the year. The real data taking started at the end of 2019 and has continued. You see that there's ups and downs in this, and this is mostly weather related. So in the southern summer, the humidity is quite high at Sutherland, and that causes a closure of the dome about halfway during the night quite often, and that's why this number is about half of the maximum. We are linked with Meerkat. So this was the aim for Meerlicht, is to be following Meerkat around on the sky. Since September last year, we can do this. So we are following Meerkat, and while we do that, we cycle through the available bands. So you get this multicolor view. At the moment, about 25% of the time is used for the Southern Sky Survey. So we didn't have the luxury that, for instance, CTF and PTF had, that, you know, there was Sloan and there was Pan-STARRS. The Southern Sky in the optical has not been fully surveyed yet to the depth that we wanted. So we had to do it ourselves. And we spent a lot of this time in 2019, 2020 doing that until we could log on to Meerkat. And that has taken most of this time, but it's good to actually do this. Here on the right, you see the field of SAXJ1808, and this may look like noise on your screen, but if you zoom in, these are all stars. You're just seeing stars, 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 stars everywhere. So that's a major data reduction and data basing task as well to do this for the whole sky. And currently, we're at the end of a complete re-reduction of all the existing data, and soon we will also have a new web interface to that data. That sky survey I was saying, so we have to do this in 6 colors. We started in the southern bit just to make sure that everything below -30 is also covered, because that's the southern limit of Pan-STARRS. And that is almost complete, and now we're going north also to have a reference frame for ourselves, of course. Sorry, sorry, this is me doing stupid things with my mouse, which I shouldn't do. So let's go back. So there's the Southern Sky survey. So you see that we do this in the 6 filters, and this broadband filter, the Q band, is the one that has most coverage because it also goes deepest. So that is good for having a reference frame. Of course, Meerlicht is a synoptic survey. So here's another projection of the southern sky, RA on the horizontal and DEC in the vertical. And what you see is that the darkness of this red color gives you a view of how much data has been taken on that specific spot. So for the grad students, we couldn't do a spot your favorite object here. But I'll spoil it and say that this is the Large Magellanic Cloud. There's the Small Magellanic Cloud. There's the, now I have to see which one is which. There's the Galactic Center, Virgo, and Fornax. And so you see all the well-known objects. Because we're not doing a sky survey, we just scan the sky, but because we are linking with Meerkat, we actually link on to those fields and observe those more often. So another view of that is that if we look at field numbers and we just tiled the whole sky, so every sky bit has its own number, we see that on some of these well-known places, like the SMC, Omega Centauri, this is the Chandra Deep Field South, which is also a very central field for Meerkat. There's more than 1,700 images already on that particular field. So this is this coverage of the southern sky is quite inhomogeneous, but you can be lucky, like this new X-ray transient that went off Maxi J1803, that actually is in a particular field that is centered on Bade's window. And so we already had a lot of data on this particular position in the sky. As I was saying, we're doing a lot of reprocessing. That is also giving us some interesting science by itself. So Ben Stapper's group at Manchester, who are part of the Meerlicht Consortium, have done a machine learning exercise on trying to identify whether a source is real or bogus. So in this sequence, you see the reference image with the core of M100 here. Then in the reduced image, clearly, any blind person can even see this. Yep, there's a transient there. This is real, and this is picked up in our data reduction pipeline. So here you see the light curve of this particular supernova that we extracted in the multicolor view. A very important part are asteroids that we want to identify because we also want to get rid of them. But in itself, it's very interesting to find asteroids in these wide field images. So we're doing a project together with ESA to actually identify these new asteroids and have an early alert system. This is done by Danielle Pietersen at Radboud. She's doing a beautiful job, and we are recovering with high purity and accuracy all the known asteroids. So this is very nice because the next step will be to identify new ones. One of the main results, science results so far has been the follow-up of GW 1908-14, where the event happened right at the start of the night in South Africa. It was fairly well localized, 38 square degrees initially, then 18.5 square degrees later. So we could actually cover this with a limited amount of fields, this error box. And we did that. We did it in 3 bands. We started immediately, and these are the earliest and deepest U-band data on this source. And we followed it for 7 nights. Unfortunately, it was full moon, and the moon was actually quite close in the sky to this location. So you see that the earlier data is not as deep as we would have liked it. And if it was like 1708-17, this is what the predicted brightness of that source would be. We didn't match that, but it was a beautiful exercise to go through, and we can still set limits on any afterglow. We mentioned SGR 1935 and the fast radio burst already, the link. And so we were part of a multi-wavelength campaign to do the optical radio at the same time. And the optical is obscured by a lot of dust in our own Milky Way. Here in the radio, you see this beautiful Meerkat image. You clearly see the supernova remnant. But it gives us very nice limits as well. I won't talk about the luminous red novae because I'm out of time, and Nadia will be talking about this later. But we did a very nice study on this one source AT2020 hat. That's it.
Thanks, Paul.
Thank you.
We have a couple of raised hands. We'll do Peter first. Peter, go ahead and unmute and ask a question, please.
Deze Peter.
Yeah, that's right.
Okay, Paul, dank je. Toen jij, oh no, I have to speak English. When you talked about your filters and the sharp edges, you also mentioned a broader band filter. Is there another mode? Does it make sense to collect all the photons over the whole band for special projects? Where you lose all color information, but you just go very deep.
Yeah, well, you actually don't go deeper because there's no open slot. But also, if you actually go further to the red, you get the emission from the night sky that actually gives you a higher background. So we chose this band, this 442-720, to optimize on signal to noise ratio and not just on signal.
Okay, thank you.
Thanks, Peter. We have time for a question by Ollie. I don't know, Joe, if we'll get to your question. Ollie, go ahead.
Hi, Paul. I was wondering how useful has the reprocessing of the mere licht data been for the future for the BlackGem data? Because I think last year you had quite a bit of time on your hands.
Yes. Yeah, thank you, Ollie. It's going to be extremely useful, if only because we can use the Southern Sky Survey as the first reference field, as a reference frame for Meerlicht. So with that, we already have a reference frame in hand, so we can use that. And also now that we have this real bogus machine learning all figured out, with BlackGem, as soon as we can get back and get it operational, we can start at full speed.
Thanks, Paul. I see Joe is typing on Slack, so I think we'll leave the spoken questions at that. Thanks again. The next talk is by David Modiano. David, I'll give you a warning after about 12 minutes if you start sharing your screen.
Yeah.
Yeah, then you're good to go.
Cool, thank you. Hello, everyone. It's great to be here. My name is David Modiano. I'm a PhD student at the Anton Pannekoek Institute in Amsterdam. And today I'll be talking to you a little bit about a project that we recently initiated called the Transient UV Objects or TUBO project, in which we search for transients in the ultraviolet. So let's jump right in. This is a Network 3 meeting, so of course a lot of you will know a lot about transients. But just to start off with a clear definition of what we mean when we say transient in general, and to show some pretty pictures. Transient is basically any kind of source that undergoes some change in its brightness. So in this example on the left, it's a supernova, a very common kind of transient that went off in the beautiful spiral galaxy M51. And depending on where the detection limit of your telescope is, you might detect the source in the quiescent state as well as in the bright state. In those cases, it's more commonly called just a variable, but in this talk, I'll just refer to them collectively as transients. So there's really a wide range of different kinds of systems that show transient behavior, and these are just some of them. So we have outbursts from accreting white dwarfs and X-ray binaries, flares from active stars, and then all the way up to some of the most energetic events that we know about in the universe, supernova, tidal disruption events, and active nuclei, among others. So there's really a wide range of different kinds of systems, which also means there's a wide range of really exciting high energy physics to be done when studying transients. And we've been doing this, as we heard a lot about in the previous talks, and we'll hear more about in the coming talks. There's now, in the last few decades, there's really been an explosion in time domain astronomy, and these are just some of the many facilities that exist, dedicated entirely or in part to searching for transients. As you can see, they really nicely operate across most of the electromagnetic spectrum. And of course, as of recently, we also now look for transients in gravitational waves and neutrinos. So this field really has now a very multi-messenger, multi-wavelength approach. However, what you might notice is that there's an outstanding gap, and that's in the UV. And while there's some facilities planned that will find transients in the UV, such as Ultrasat and Dorado, so far none exist. And it turns out that this matters. So although we do many follow-up studies of transients in the UV that were discovered at other wavelengths, for many kind of phenomena, not looking for them in UV means we miss early UV data. And that early UV data can sometimes be really important in understanding really the physics that's underlying the outbursts. And the reasons for that can be different for different kinds of sources. So I'll just mention a couple of examples in this slide. So here you see a light curve from a dwarf nova. This is an outburst from an accreting white dwarf. And the UV emission of these sources is not very well understood. And that's in part due to a lack of that early data. And the UV emission, though, is very important because it's probing the inner regions, the hot inner regions of the accretion disk. So we really need it to be able to understand what's at the heart of these processes that are causing the outbursts. But what I also want you to pay attention, what I also like you to pay attention to in this figure is that in this peak part of the outburst, the UV, which has been offset in this figure by 2 magnitudes, is actually much brighter than the optical. And we've seen this over many dwarf nova sources. So the UV is actually a good place to look for these sources in general because, well, they're brighter than the UV, so we can find more of them, we can go deeper. Another different example is in a pulsating variable star, so like an R Lyra type. So here you can see 3 simultaneous light curves. The top is optical, the middle is near UV, and the bottom is in the far UV. And you can immediately see that the UV behavior is really very different from the optical in that the variations are much stronger. And again, that means that if we look for these sources in the UV, we're more likely to find them. We can find more because in the optical, we might not always be as sensitive. So these are just 2 examples, and I won't get into supernova and tidal disruption events, but it's worth mentioning that there's some really cool reasons why looking for these sources in the UV to begin with is really interesting. So if you're interested in that, do ask me about that later on. But perhaps the most intriguing thing about looking for transient EUV is that it hasn't been done before. So every time we look for transients at a new wavelength range or in a new messenger, we've ended up discovering completely new kinds of sources or revealing new behavior of sources types that we didn't know about. So it's worth exploring just because it's a parameter space that we haven't looked into yet. So the idea of the TUA project is that we can do this already without a UV dedicated transient searching facility. What we do is use currently operational UV facilities to look for UV transients in almost real time. And by that, I mean hours to most a few days. So to do that, first, we need a UV facility with real-time data that we can access quickly. And for that, we use the ultraviolet optical telescope aboard SWIFT. And I'll say a bit about that in the next slide. But the second thing we need is, of course, a method to process that data to look for transients efficiently. And for that, we use TUA pipe. So this is a pipeline that we developed within our group, and these are the people that are involved in TUA project and in development of the pipeline over the last few years. So I'll spend most of this talk talking about how the pipeline works and some initial results that we got from it in this testing phase. But first, a word about the data that we actually use. So SWIFT was a space-based is a space-based observatory that was launched back in 2004 with the aim of finding and studying GRBs. So it's equipped with the BAT to find the telescope to find the GRBs, and also with an X-ray and UV optical telescope for follow-up. And the UVOT is the instrument that I'm most interested in. And the key thing about SWIFT, which is actually almost unique about SWIFT, is that all the data are accessible to the public within a few hours after they've been taken, which means that anyone can look at the data to look for transients in almost in real time. And this is the idea of our project. So now I'll take you through a little bit of how our pipeline works and what it does before moving on to a couple of the initial results we got. So we run TUA pipe every day. And it starts by downloading all new UVOT data that was taken. So that would be all data taken by UVOT in the previous 24 hours up to the last few hours before. And these are the science images. And for every science image, we look for transients using image subtraction. I won't go into the details of how image subtraction works, but at a basic level, it is what it says it is. You take 2 science images and you find the difference, the resulting difference image. Any source that pops up, such as this one, is indicative that a source changed brightness in the 2 science images, so you have a transient. So next, our pipeline moves on. For every transient that it finds, it goes back to all the SWIFT, the UVOT data, it goes back to the science images and creates light curves of the source. So in this example, we detected a transient in recent UVOT data, as you can see from this detection, and went back and created a light curve from all available SWIFT data. And this is one of the reasons why SWIFT is so great for this, because it's been operational for so long and there's really a lot of data in the archive. So you can really look at the long-term UV behavior of many of these sources. In this case, for example, we found that there was no previous UV outburst of this source, but this is a very useful tool for trying to understand past UV behavior. Have there been any previous outbursts? Is there any periodicity, etc. So it's worth mentioning that the dual pipe has really been in development for the last few years, but it's now reaching the end of that development and really being finalized. And so there'll be a paper coming out about the pipeline in the next few months. So do stay tuned for that. So just to give a sort of general overview of what we've processed so far. In an initial 6-month testing period last year, we processed over 40,000 images. And that's virtually every image that was observed by UVOT because we run the pipeline every day. And for rates, we get a few tens of UV candidate transients every day. And most of these are identified as variable stars and binaries, outbursts from accreting white dwarfs and active galactic nuclei. So some of the sources that I mentioned at the beginning of the talk. But a few of these have no previous identifications and have not been classified. Or perhaps they're sources that have been classified, but have we detected some new outburst that has not been reported so far. And these are the sources that we're really interested in. Because we want to find new transients and we want to find new behavior of known sources. And so these are really the prime targets for the TUBA project. Yeah, I didn't mention this plot. This is of all the fields that were observed by UVOT. As you can see, because it's a space-based observatory, they're scattered nicely throughout the sky. So once we have these interesting transients, what do we do with them? The next step is to further investigate these sources, to first try to classify the ones that are not classified, and then study them, try to characterize them, understand something about the outburst properties, which will ultimately help us understand something about the physics that's causing the outbursts. So to do this, we've recently started implementing our follow-up strategy, which revolves mostly around ground-based spectroscopic follow-up. So where we try to take spectra of our sources only up to a few days after they've been, we detect them in the UV. And to do this, we have ongoing programs in the last few months and in the coming months with 3 different facilities in different locations around the world. So already analysis for some of those observations is underway, and we have some more planned. And another option is to take further photometric observations. So this could be with, for example, other telescopes at the Southern Observatory in South Africa, but also with SWIFT itself. The UVOT has 3 optical filters and 3 UV filters. And for example, we could ask for further photometry with all the filters in order to get some color information for our sources and be able to classify them more easily. So as I mentioned, the pipeline was really in development stage, but we're kind of exiting that stage. And in the initial test phases, we already got some nice results. So I'll just finish with a brief description of a couple of these. On the left, there's a UV light curve of, a source detected in October of last year with dual pipe by Silverbene. So this was an interesting result because the source was a CV candidate. And with DUA, we detected the first UV outburst of the source, and looking at the outburst properties, mainly the increase in brightness, as well as the duration of the outburst, we're able to confirm this as a dwarf nova outburst of a CV. More recently, in February of this year, we discovered a completely new CV due to its UV outburst, as you can see from this light curve that was produced by TUVO. And this source had no previous identifications at all. So we suspected there was a CV from the outburst properties, but there was no other information about it. We were able to take a salt spectrum, which you can see down here. And from the characteristic hydrogen and helium emission lines, as well as the overall shape of the spectrum being flat and indicative of accreting source, we're also able to confirm this as a CV. So that's everything I have to say. The take-home message here is really that the UV wavelength range has not been significantly used to search for transients serendipitously. But if we do start doing this, we can really lead to a much better understanding of the physics that's causing these really interesting high energy outbursts that we see with transients. But perhaps even more excitingly, we could discover completely new kinds of sources. We haven't looked systematically in the UV and large scale yet, so we don't know what's out there. And the idea of the TUA project is to try to start filling this niche a little bit by looking at UVA data to look for transients within a few hours to a few days with our custom built pipeline. And we're now exiting the development stage. From the initial results, we can already see that there's some high potential for some interesting discoveries. So we're very excited to see what comes out in the next few months and years. Thank you.
That's very exciting, David. Thanks so much for introducing that project to us. Couple of questions, maybe. I already said earlier that the first student to ask a question, I will buy them a bottle of wine. And I should have said that Olly Boersma was the first to do that. So I'll make sure he gets one. And I was going to say that the next person will also get one, but it's Ines. So now the third person will also get a bottle of wine. So Ines, please start.
Hi, David, nice talk. So I'm curious about the plot where you show the variables you've detected with TUFO. There are plenty of sources that seem to be on the galactic plane, but there were also quite a lot that are outside of the galactic plane. So do you think many of those are extragalactic, or are they mostly galactic?
Yeah, it's a good question. So it really depends. Most of those will still end up being galactic because there's just so many variable stars in the galaxy, for example, like the R Lyrae or different kinds of variables eclipsing binaries, that a high number of these will still be nearby galactic sources. But it can also be extragalactic. So we also detect things like AGN and so it's really a mix. We have of course, no control over the pointing strategy of Swift. So it just points wherever it needs to follow up the sources. And so the range of kind of sources that we can find is really across the board.
Thanks.
Thanks, David. Quick question from my side before we continue with the next talk. You mentioned that maybe a dozen or so candidates come in every day. Can you explain to me how you then sift through these? Is this by eye? Is part of it automated? How does it work?
Yeah, so so far it's still by eye. So the numbers are manageable enough that we just look at them by eye and try to determine well, what kind of sources they are, because we also match each source to different catalogs automatically, so we can immediately see this is already classified, this is not that. So far we do it by eye. Yeah, there's we have some ideas to implement some programs to already do some period searches, for example, and then we can classify sources automatically. But so far we haven't done that.
Well, if the numbers are manageable, I think that's a very sane strategy. So thanks again, David. If there's more discussions warranted, you can all continue it on the Slack, as I see has been happening for a few of the previous talks as well. So next up is Deepak Erpakchan, and we go this afternoon through the whole range of wavelengths, and now going for X-ray transients. So Deepak, take it away, please.
Thanks. So I'm Deepak Erpakchan. I'm a PhD student at Estron and Radboud University. I'll be talking about the origin of fast X-ray transients. This is a work which I've done in collaboration with the people shown on the screen. So what are these fast X-ray transients? So these fast X-ray transients are high energetic astrophysical phenomena. These are very fast transients over the time scales of hundreds to few thousands of seconds, which last over the time scales of from hundreds to few thousands of seconds. There have been around 30 FXRTs, which has been discovered from Chandra and XMM Newton archival data, and also from Swift and eROSITA observations. So this has been discovered through the systematic searches in the Chandra and XMM Newton archival data. So in the figure given here are the X-ray light curves of two fast X-ray transients. The one shown in the left is XRT 210423, which is a recent FXRT which was reported this month on 4th of May, which was actually found in the Chandra archival data, occurred on 23rd of April. It shows very similar light curve to that of which seen in CDF XT2, which is X-ray transient reported by Siu et al. In 2019. The bottom panel shows the hardness ratio of this events. So coming to the comparison plot for this fast X-ray transients, shown in the figure are the CDF XT2 and FXRT 210423. These are the fast X-ray transients, which was shown in the earlier slide, in comparison with the short GRBs, also with a supernova short breakout X-ray light curve, a TDE, and also in comparison with GRB 17018, 17A afterglow. So what are the possible origins of this fast X-ray transients? It could be one of the possible origin is the white dwarf intermediate mass black hole tidal disruption event. So the compactness of the white dwarf and the comparably low mass of the intermediate mass black holes could have produced like shorter X-ray flashes, which we might be seeing as this fast X-ray transients. And in the case of particularly in case of one FXRT, which is XRT 005 and 9, it shows precursor event before the main flare. And the time scale is in agreement with the white dwarf tidally disrupt white dwarf orbit around an intermediate mass black hole in an eccentric orbit. So this all suggests the possibility of this FXRTs could be due to the white dwarf intermediate mass black hole tidal disruption event. Another scenario is a binary neutron star merger that the FXRTs could be produced by binary neutron star mergers. The X-ray plateau that we see in the light curves of this fast X-ray transients are quite similar, are also seen in some of the short GRBs. So this plateau seen in the X-ray light curves, as well as the host properties that which I'll be discussing shortly, shows the association of this fast X-ray transients with the binary neutron star mergers. So this is also a possible origin of this fast X-ray transient. Another one is a supernova shock breakout. This could also be a probable origin. And there was an event reported by Soderberg et al. In 2008, where the X-ray flares were clearly associated with the supernova, and which was having a peak X-ray luminosity of 10⁻43 ergs per second. One thing to keep in mind is that the luminosity scales of the peak X-ray luminosity in the case of supernova shock breakouts is much lower compared to that of in the case of binary neutron stars, and as well as intermediate mass black hole white dwarf tidal disruption events. So are there any counterparts for this fast X-ray transients? Unfortunately, no, not yet, because of the fast nature, and because most of this FXRTs are found through the systematic searches in the archival data. There have been no optical or near infrared counterparts so far. The closest which we came was for the CDF XT1, which was reported by Boyer et al. In 2017, which is a Chandra Deep Field South X-ray transient 1. There was a VLT observations 80 minutes after constraining upper limit of 25.7 in the R band. Shown in the figure is the deep optical WHD Z band images for the recent FXRT, that is 210423, which was reported this month. So we took the we looked into the field of this particular fast X-ray transient. So without the counterparts, how are we gonna know about the nature of this fast X-ray transients? So the host properties are very important to understand what are the possible origins of this FXRTs. So the multi-filter observations of the field of this fast X-ray transients could tell us about the the color associated, the color and also the offsets associated with this event. That gives a lot of information about the origin of the fast X-ray transient. For instance, a younger progenitor or a younger associated host would indicate to a shock breakout scenario, while an alt progenitor or an alt stellar population would have a much closer association with a binary neutron star or an IMP-HTDE. And also the offsets gives us tells us about the binary neutron star scenario. There have been around 12 FXRTs reported by Alpan Larsen in 2020. They favor the scenario of supernova shock breakout. Here in the figure shown are 2 FXRTs reported by them. The upper one, the green circle here shows the FXRT uncertainty region. And in the upper panel, upper figure, you can see that for that particular FXRT, it is associated with the underlying host. So it probably could be associated with a TDE, for instance, in this case. And the other one is a hostless scenario, the FXRT in the bottom panel. So it could be a binary neutron star merger. Just to emphasize on how important the host galaxy information are, this was the case of CDF XT2, which is Chandra Deep Field South X-ray Transient 2, reported by Xu et al. In 2019. They had the host galaxy information, and the red circle shows the X-ray transient uncertainty position, and it's around 0.44 arcsecond away from the host galaxy, and that is at a redshift of around 0.73. That would mean a projection of around 3.3 kiloparsec, and that is very much in agreement with the offset that we see in the case of binary neutron star mergers. Coming into the XRT 005 and 9, so we observe, we have deep optical observations of some of the fast X-ray transients, and I would like to show one of the 2 of the FXRTs having deeper optical observations. So this XRT 005 and 9 was a FXRT reported by Yonker et al. In 2013. This was found in the direction of M86. It was found very close to a tidal stream of stars flowing out of stars, which was caused due to maybe due to a recent merger with an SDSS galaxy. So it was found very close to that tidal stream. And considering the FXRT to be associated with the M86 at a distance of 16.2 megaparsec, that would give us a peak luminosity of around 10^42 ergs per second. Yeah, so we also explored the possibility of it being associated with a galaxy cluster. Like for another FXRT, which was reported by Glennie et al. In 2015, it was found to be associated with a galaxy cluster. So we probed the possibility of it being associated with a galaxy cluster, and we obtained the redshifts of this galaxies, and particularly we only got for one of it. But assuming a galaxy cluster at a redshift of 0.19, it have a peak energy of 10^46. So it is very essential to understand to constrain the distance to this FXRTs to understand the nature of this FXRTs. Just a bit more on the deeper image of this, which we obtained from VLT4's observations. There was a source, a northwest source close to the 1 sigma uncertainty region of the FXRT. Which is indicated by a white arrow out there. It was having a magnitude of 25.9. And very recent observations with Hypercam reconfirmed our findings of this northwest source. which is shown in the right panel. The one good thing about HyperCam is that we have it's a wonderful instrument which have simultaneous UGRIs at band observations, and we would get a photometric redshift which would help us constrain the luminosity. And finally, just to mention about the recent FXRT which we followed up, it was 210423. We have observations using WST, FOSS, and HyperCam and GTC. And so in the left panel shown the FOSS image. The red circle shows the 2 sigma uncertainty region, and there is a probable galaxy 4.6 arcsecond away from the transient uncertainty region. And we obtained the X-shoot spectra using X-shooter and found that it's at a redshift of 1.51. That is a projected distance of 38 kiloparsec. And the peak X-ray luminosity is around 10 power 45 ergs per second. And our HyperCam data also shows a probable source near to the FXRT transient position. So just to conclude, this FXRT is a high energetic, new energetic astronomical phenomena, and the possible origins include binary neutron star mergers, white dwarf IMP-HDDs, and supernova shock breakouts. And it is very important to understand the host properties of these FXRTs in order to find the possible origins. And being a binary neutron star being one of the possible origin, this could be an excellent prop for distant binary neutron star. Thank you.
That is very exciting, Deepak. That HyperCam data is amazing. Sometimes in the Force 2, I wouldn't have believed there was anything there, but it was very convincing.
Yeah.
I see a question by Harish Vedanthan.
Yeah, I have a question about the possible progenitors. And if the luminosity is 10 to the 45 ergs per second, then wouldn't it be many times the Eddington luminosity of 10 to the 4 solar mass black hole? That's one thing. And for the other options, which is like a binary neutron star merger, which you mentioned, does it roughly agree to an order of magnitude with the all-sky rate of short gamma ray bursts corrected for beaming, let's say? So all-sky rate of binary neutron star mergers.
Mm-hmm. The second, so I missed the first part. Sorry, the second part, we haven't compared the rates yet, but the rough rates of this FXRTs are about 10 power 6 events per whole sky per year. And I think the first question was about
10 to the 6 is plenty.
Yeah.
I mean, in fact, it's too much compared to the.
Yeah, it's too much. Yeah,
it's too much. I would say that's the problem. The first one was: isn't the luminosity far higher than the Eddington luminosity for an intermediate mass black hole?
No, it would be within the intermediate mass black hole white dwarf range. The IMP-HW, the tidal disruption event could have the peak luminosity can go up to 10 power 51 ergs per second. For a beamed case, maybe, but it's well within the WDIMPH scenario.
Okay, thanks.
Thanks, Deepak. That was very exciting. We got to continue. We're still good on time. Thanks again. We'll go to the next talk by Nadija Blagorodnova on luminous red novae. So let us see if we get the screen sharing started up. There we go. Nadja, you take it away whenever you're ready.
Great. Well, thank you. Well, hello, my name is Nadja Blagorodnova. I'm a Veni Fellow at Radboud University. Yeah, and I thank the organizers for giving me the chance to talk about the coolest transients, luminous red novae, and their role in actually teaching us to, to show what's actually happening when a binary ejects its common envelope. So just a bit of background on what the common envelope is. And this phase was already postulated in the late 70s that it's a necessary phase to bring a population of binary stars, which are born with initial periods of days to years, to a final compact configuration that we see some compact systems of minutes or hours. So there have been a lot of theoretical work on this topic because we really want to understand what's going on. And well, we believe that there are like several stages in which this binary starts interacting. So in the first phase, well, the primary generally starts to transfer mass into its secondary companion. And this mass transfer can last a certain amount of years, up to the point that basically this kind of cocoon or envelope forms around these two stars. And at the point when this cocoon is no longer co-rotating with the binary, then basically the secondary star will start to kind of in spiral towards the core of the primary star. And this in spiral will transfer the angular momentum from the orbit of the binary into this gaseous envelope. So what will happen is that basically like in a blender, when you switch it on, right, like all this gas will start to expand. And this also can last for a certain amount of years until we are left basically with this tight binary with the naked core of the primary star and the secondary companion in a very close by configuration. So this is kind of the theoretical pictures that we have. There have been lots of like simulation and theoretical work, but can we actually observe it in real time? And here is the cool part is actually we can observe it. And we can observe it with this type of transients called luminous red novae. And so far, what we know from the observations of luminous red novae is that these are failed common envelope ejections. In most of the cases, what we see is that part of the envelope is ejected in these very red transients that you can see here, like VA38Mon is a very well-known example. And this is like a beautiful HST image of the light echo also surrounding this, this nova. But what we believe is that like actually the binary ends up merging. So like only a fraction of this envelope is ejected. So where do these transients live in this kind of parameter space? So if we see the characteristic timescales in the x-axis and their magnitudes, we can see that they're called kind of gap transients because they are located in this kind of region in between the core collapse supernova and the classical novae. And also we see that kind of the timescales of the events also increase with the brightness. So the brighter the event, the longer it lasts. And for surveys such as like ZTF or Black Gem, we basically are able to detect these kind of transients up to distances of like 100 megaparsecs, for example. So if we have a closer look at the morphologies of these transients, what we see is that there are no equal luminous red novae. They kind of all seem to morphologically be different, but we see that they tend to have these kind of two peaks. One is like a faster blue peak, and the second was like, it's called red peak because of the redder colors the nova takes, and it's kind of like a more extended plateau or a secondary peak. So let's have a look at luminous red nova some years before and some years after this outburst. And here's my basically my message to take home. I really want you to believe that luminous red nova are great to understand the physical processes that occur around the ejection of the envelope in binaries. So in this light curve, we can see that there are several parts. The first of all is this quiescent progenitor that we can detect like kind of 10 years, 15 maybe years in archival data before the outburst happens. Then the next phase is this precursor phase where we see that the progenitor system slowly brightens up. It may show some variations, but generally the system becomes brighter. And then these outbursts happen. And as I mentioned before, we have like a faster blue peak and then kind of a slower red peak. So what this tells us about what's going on in the system. So the first of all is that the progenitor can be used to understand the population of binary systems which are experiencing unstable mass transfer. So this progenitor system is related, you can use it to infer, like for example, the masses or the evolutionary stage of those binaries that are becoming unstable. The next phase is the precursor, and this also tells us that at that point, the system becomes brighter because it's likely experiencing lots of outflows. And these outflows are related to mass loss from the Lagrange L2 and L3 points And that means that the system is losing mass and also angular momentum. And what we believe is that this loss of mass really shrinks the binary to the point of like, you know, the secondary kind of piercing into the envelope of the primary star on a matter of like a few years. As you can see, well, the precursor only lasts like a couple of years, maybe 5 years. Then this fast peak is related to the cooling of the ejecta that you know, is being ejected when the secondary penetrates the envelope. And the final plateau or the secondary red peak is related to the shocks that this ejecta experiences when it collides with this previous mass loss disk around this binary system. So actually observing like a luminous red nova from the beginning to an end really can tell you a lot of you know, the physics that are happening in a binary system when this common envelope is ejected. So here I'm going to use an example of a luminous red nova that was detected in NGC 45 in 2018. So as we can see here, there is a beautiful HST image. And if we zoom in and in and in, we can see that there is a little star there that actually was observed in several filters. We can also use the Spitzer archive or the WISE data to search for like mid-infrared counterparts. And we see that before the outburst, there was nothing there. However, in 2018, after the outburst, there was a new source detected, which was related to the newly formed warm dust in the system, because basically the ejecta is kind of expanding and it's cooling really fast. So it really forms a lot of warm dust. So what can we do with the progenitor data? Well, the easiest thing you can do is to use the HST data to model the SED of your progenitor and put it on a single stellar evolution track to determine how massive was the progenitor and what was the evolutionary stage. So in here, we can see that different methods also agree, like the progenitor was likely about an 11 solar mass star, which was in the gap. So basically this star was leaving the main sequence and it was becoming a red supergiant. And here is exactly where we expect kind of the unstable mass transfer to happen. So up to this point, like everything makes sense. So we also can use the mid-infrared non-detections that we had before the outburst to actually put a constraint on how much dust or how much mass there was around the system at the point of the progenitor. And we actually see that we can put like very tight constraints, especially for warmer dust. And we can see there was like not much mass around that progenitor up to like 13 years before the outburst happened. However, this was a binary, right? So in this work, we actually took the right approach. So we decided to model the progenitor as a binary system. And as you can see here, the actual primary stars, the donors, are more massive. So they actually go from 12 to 16 solar masses. And at a certain point, they start transferring mass. And at this point, which may last up to around like 400 years, as in this case, we see that the system becomes less and less luminous because basically the star uses part of its energy to actually readjust to the loss of mass. So basically, more massive progenitors appear as less luminous, so they fit kind of the locus of this progenitor star. So we can also observe the transient. We can follow up in the optical, as here we can see it only lasted about 70 days, but the mid-infrared emission, as you can see here in the top, lasted for like several years. We can also observe this in spectrum. For example, the H-alpha profile also tells us, like, for example, the velocity of the ejecta. And if we put our progenitor estimation in this diagram with the peak magnitude, we actually can see that along with other luminous red novae, there is a correlation between of how bright the nova is and how massive the progenitor were. So actually, well, this also makes sense because likely the more massive progenitor eject a greater amount of mass, so the transient is actually brighter. So what else can we do with the transients and with our progenitor modeling? Well, the standard common envelope formulas actually tells you that in this exchange of orbital energy, you unbind part of the envelope when the secondary spirals in. And basically, you also give some kinetic energy to this part of the envelope that you are ejecting. So there is kind of a balance of the orbital energy that you lose and this unbinding of the envelope. So by modeling our progenitor, we could estimate that the ejecta mass in this case for our transient was about 0.15 to up to half a solar mass. But then we also saw the transient itself. So we could model its luminosity, its temperature and radii. And for example, we derived like a plateau luminosity of about 10 to the 40 ergs, velocity expansion for the ejecta, and the duration of the plateau. So then we used these parameters to model the ejecta mass using two different approaches. One is the scale type 2 supernovae, and the other one is the shocked power emission. And they also gave very similar results. So my conclusion here is that luminous red novae are great tools to study those binaries that become unstable. They can teach us about what's happening in the mass transfer in those systems. And we know that this L2, L3, it's a really important mechanism in like draining the angular momentum from the system. And finally, we see that actually the transient characteristics also give us insight about the progenitor population, even though maybe we don't see them. So yes, future surveys, like BlackGen, we are looking forward to detect more of this to learn more about mass transfer in binaries. Thank you very much.
Nadia, those are some very amazing and interesting systems. Thanks for explaining your research to us. Questions? Raise your hand in the Slack, in the participants panel, or put something in the chat. Hey, so Nadia, in the meantime, I guess for AT 2018 BWO, part of your results stem from the 2004 non-detections with Hubble. So how lucky do you need to be that there's old data that gives you an upper limit from what happened with the progenitor?
Right. So yeah, it depends on the distance, right? So yeah, I think a great portion of these systems should be in Hubble archive. Mm-hmm. If the progenitors, let's say, are more massive than 10 solar masses, and we are going up to distances of up to like 20 megaparsecs. Mm-hmm. So like the majority of them should be already in the Hubble archive, because Hubble, has been covering lots of like nearby galaxies. So we should be able to put constraints on that. But as I mentioned, like we can detect them up to like 100 megaparsecs, and then that's a bit more of a challenge. So.
Yep, thanks. So any final questions for students to win a bottle of milk, Fernandez, or wine, whatever you prefer? It's either now or in the next talk by Kenzie that you have your last chance of winning those. So I'm looking at the participant screen, and I think we are covered and done with the questions, and we're still on time. So thanks again very much, Nadia.
Thank you.
We will continue with the final talk of this session, which is by Kenzie Nimmo. I see the first slide already appeared, and so Kenzie, go right ahead.
Great, thank you. Hi, I'm Kenzie. I'm a third-year PhD student at the University of Amsterdam and Astron. And today I'm going to talk to you about probing fast radio bursts on sub-microsecond timescales and other results from our research group. So first, what are fast radio bursts? Fast radio bursts are extremely bright, short duration flashes of coherent radio emission that come from extragalactic distances. Some fast radio bursts have been seen to repeat, and others have been seen only once. The repetition is clustered, so we have periods of activity and inactivity, and the activity level varies quite drastically between different sources. It's currently unclear whether there are different types of FRBs, if there's repeating and non-repeating distinct classes, or even more characterizations of FRBs. But the overarching questions are, we don't know what objects produce fast radio bursts, and we don't know what the emission physics is. So to put it into context here, I have the transient phase space diagram where we have luminosity on the y-axis and duration on the x-axis. I show the pulsars and rotating radio transients from our galaxy in pink here. Some pulsars produce giant radio pulses where the luminosity is higher than the average pulse. So here are the crab giant pulses in orange. And then some crab giant pulses resolve down to individual isolated nanoshots, so nanosecond duration, high luminosity shots, which are shown over here.
Is it just me?
Nope. No, I think
no, doesn't sound like that.
Okay. We'll give it a minute, and otherwise I'll ping Kenzie in the Slack.
Well, if the internet connection is gone at her end.
Well, what more can we do?
WhatsApp?
Yeah, I think we're restarting. Jason or Ines, or can someone? I think she's not. She knows by now, but if someone could WhatsApp her. We'll give it a minute.
We also have a question for Deepak on Slack.
Deepak, are you behind the terminal and available to answer a follow-up question by Harish?
Yes, I'll look in the Slack. Yeah, sorry, I didn't.
Oh, no worries. We have time now, so we might as well just put you on the spot and ask you live.
Hi, sorry. I think.
Oh, no worries, no worries. So let us just.
Should I share my screen again?
If you wouldn't mind, we didn't miss. I don't think we lost a lot of time. So.
Okay, I'll just continue where I was, and then I guess ask questions if you misunderstood anything. Okay,
I think we're good. So go right ahead.
Sorry. Okay, so this galactic magnetar SGR 1935 last year produced a really bright radio burst that's many orders of magnitude brighter than any other radio burst that we've seen from the Milky Way before. So this is this event here, which was detected by both CHIME and STARE-2. Independently and at different observing frequencies. And you can see the luminosity is 1 or 2 orders of magnitude weaker than the general FRB population. Shortly after this detection, FAST in China detected this really weak burst, which is more comparable in luminosity to pulsars and rotating radio transients. And we were monitoring with Westerbork RT1, and we monitored for hundreds of hours and detected 2 bright bursts that were separated by only a few seconds. Now, this is interesting because it showed that there's not a clear distinction between FRB emission and maybe weaker, more regular magnetar emission, and actually the luminosity spans 7 or 8 orders of magnitude. So the most promising model is magnetars. Magnetars are highly magnetized neutron stars where the source of the energy comes from the decay of the magnetic field as opposed to spin down or accretion or heat. And because they have such a strong magnetic field, they have a huge energy budget, which is what we need if we want to produce these high luminosity bursts. So what we're doing is we're performing follow-up of CHIME repeating FRBs with the European VLBI network. So CHIME is shown here on the left. This is basically an FRB finding machine. It's found so many FRBs, including published about 20 repeating FRB sources. And so we work in collaboration such that they detect an interesting source, and we follow up with the EVN, which is a global network of radio telescopes. And we use the really long baselines to spatially localize the bursts with extremely high precision. And we also use the baseband data from the individual stations to study the burst properties in very high detail. And so I'll present results from specifically two repeating FRBs for this talk. The first is FRB 2018-0916b. Using the EVM, we localized this burst with an accuracy of 2.3 milliarc seconds. And we see that it is inside this spiral galaxy at a distance of 150 megaparsecs. And not only that, but we could actually identify that it's in the arm of the spiral galaxy and also is very close to this prominent star forming feature in the arm of the galaxy. This was the second repeating FRB to be localized, and the host and local environment looked really different from the first repeating FRB. Which was found in a dwarf galaxy a low metallicity dwarf galaxy at a distance of about a gigaparsec. We also, so this is a Gemini North image, and we also followed up with Hubble to have higher resolution in the optical, and we can see that the position of FRB 180916 is slightly offset from the nearest star forming knot by about 250 parsecs. The second repeating FRB I'd like to talk about today is FRB 2020-0120E. This FRB was recently published by the CHIME team, and it's specifically interesting because it seems to be coming from the direction of M81. Now, M81 is a really nearby galaxy at about a distance of 3.6 megaparsecs, so this is really, really close compared to other FRBs. And in the discovery paper, they were unable to confirm whether it was associated with M81 or whether maybe it was coming from within the Milky Way, but they could rule out it coming from much farther than M81. So this source is extremely close. This red ellipse is the error region from CHIME. This is the discovery error region. And within this, they identified 4 sources of interest, which is an H2 region, an X-ray source, a globular cluster, and a radio source. And because the red ellipse is so large, they couldn't say if the FRB was associated with any of these and which one it's associated with. And so with the EVN, we were able to precisely localize FRB 2020-0120E to a few hundred milliarc second accuracy. This is work that's led by Franz Kirsten and Benito Marcotti. And with this precision, we could confirm that the bursts are in fact associated with M81, and in fact, they're coming from the globular cluster. So again, this is a different environment from the other precisely localized repeating FRBs. And this diversity in host and local environments has to be accommodated in the progenitor models. So either you have many different astrophysical objects that are producing fast radio bursts, or you have one type of object that can live in many different types of environments. Going back to magnetars can be created through many different channels, and so they can live in many different types of environments. So this is consistent with this picture. Here, though, it's difficult to reconcile FRB 2020-0120E, the association with this old stellar system in a model where you have a magnetar that was created through the normal core collapse formation channel. So maybe instead we have a magnetar that was created through accretion-induced collapse, or maybe through a binary merger. So now I'm going to switch gears a little bit and talk about the bursts themselves. I mentioned at the beginning that we don't know if repeating and non-repeating FRBs are physically different objects in emission physics, but we are, however, starting to see this characteristic picture emerging for repeating fast radio bursts that in general non-repeating fast radio bursts don't exhibit. So for 2018-0916, we see that the bursts are narrow band. They don't extend the whole frequency extent. We also see this sad trombone effect, which is most evident here, but it's basically when you have subbursts that drift down in frequency as a function of time. Additionally, so here we have the burst that we detected with the EVN. We have the black, which is Stokes' I, red is linear polarization, and blue is circular polarization. And we see that they are 100% linearly polarized, 0% circularly polarized. And the polarization angle, which is in the top panel, is constant during the bursts and also between bursts. These properties are also seen for the first repeater, FRB 121102, which is why we think that there's this characteristic picture emerging. And these are the 4 bursts that we use to localize FRB 2018-0916b. And I'm going to talk about this burst in particular, B3. So this is the same burst at 64 microsecond resolution. We then go to 16 microsecond resolution, and then even a step higher to 1 microsecond resolution. And we zoom in on these 2 regions, and you can see that the burst resolves down to 3 to 4 microsecond structures. Not all of the bursts, however, resolve down to these microsecond structures, and we do see a range of timescales where the dynamic range is about 500. Additionally, we see on these timescales, we see small variations in the polarization angle, and we argue that potentially these are characteristic of repeating FRBs. For this source, we were limited by scattering in the Milky Way interstellar medium. So you can see here that it's in this really bright red patch of high scattering. But this other FRB, 2020-0120E, is at much higher galactic latitude. And so it means that the scattering effect is much smaller. And so this means it's really promising to study really high time resolution structure in the bursts. So here I show the 4 bursts that we used to precisely localize 2020-0120E to the globular cluster. As you can see in the dynamic spectra and the profiles, it matches the criteria for a repeating fast radio burst. The plots here are at 8 microsecond resolution. Thank you. Are at 8 microsecond resolution, which is already really high time resolution. And you can see that the polarization angle does vary on these timescales. So we see this as well. And then finally, I'm gonna single out burst B3 here, where I've now plotted it at 1 microsecond resolution in green, which is the same resolution that we plotted the previous FRB. And then also at 31.25 nanosecond resolution, which is the highest resolution we can get with the data. And I've got some zoom ins of the yellow and the blue regions here. And we see that there are structure down to about 60 nanoseconds in this burst, which is 2 orders of magnitude smaller than we saw for FRB 2018-0916B. Similar to 180916B as well, not all of the bursts resolve down to these isolated shots, and we do see a range of timescales with a dynamic range of about 1,000, so completely consistent with this other repeater. This forest of shots that you can see here really resembles what we see in the Crab pulsar. So this is an example of a Crab pulsar giant pulse, where you can see the same kind of forest of shots in the burst. This is a zoom in of a subsection of this. Okay, so I'm going to bring this back finally from the beginning of the talk, but now I'm going to add on the timescales that we see in 180916 and also in 2020-0120E. FRB 2020-0120E exhibits the kind of repeating FRB properties that the other repeating FRBs show. So there is a connection to the population of repeating fast radio bursts. The forest of submicrosecond structures resembles what we see in the Crab pulsar. And also these isolated shots have about the same brightness temperature, where the gray lines are constant brightness temperature, as the highest luminosity Crab nanoshots. Also, similar to the Crab, we see many different timescales in FRB 2020-0120, where we have this microsecond level timescale, which is consistent with what we see from the Crab giant pulses, although much higher luminosity. And then finally, these wider components have 1 or 2 orders of magnitude lower luminosity than the bright burst from the galactic magnetar. So this source really bridges the gap between extragalactic fast radio bursts, young pulsars in the galaxy, and galactic magnetars, and supports that we have the common magnetically powered emission mechanism spanning many timescales and luminosities. So yeah, my conclusions and my summary, the main points are that FRBs live in a very diverse set of host galaxies and local environments, which supports that they originate from magnetars created through many different channels. We see short timescales in both the FRBs that I presented here, which implies that we have a really small emission region of less than 1 kilometer. This supports the idea that we have the emission coming from within the magnetosphere of the neutron star as opposed to much farther out. And then finally, I've shown that FRB 2020-0120 is connected to extragalactic repeating FRBs, the Crab pulsar, and also the galactic magnetar SGR 1935. And so this supports that they're all powered through magnetic energy, and potentially the FRB is the result of magnetic reconnection in the magnetosphere of a highly magnetized neutron star. Thank you very much. And sorry for the technical troubles.
Thanks, Kenzie. I felt that you picked that up very nicely again after the glitch. So all good. And it was the last talk of this session. So that was a very nice finale. We have a couple of questions. We'll start with Jacco.
Hi, Kenzie. Nice talk, nice results. I'm wondering about the short timescale saying that it should be a small emitting region. If you have coherent emission, And if you have a very beam thing, maybe this doesn't hold, right? If it's just a very narrow spot near the light cylinder, that might be possible as well.
So do you mean like a relativistic argument?
No, basically a beaming argument. If it's coming from one tiny spot on the light cylinder, right? So it's what you assume if something is isotropic, yes, it should be a small region. But if it's a very directional one, and if it's coming from a small region in the magnetosphere, I think that is still possible, given that this is very coherent emission.
Yeah, but wouldn't the emission region still be small by that argument, even if it's beamed? The emission region.
I think that's true, but I don't think that you can say that it shouldn't be further out from that argument.
Oh, okay. So yeah, the kind of competing models, at least in fast radio bursts, is that you have magnetospheric emission, and then the non-magnetospheric emission is where you have like a flare from the magnetar that creates a shock that interacts with material in the surroundings. So then you would have to invoke clumpiness in the material to be able to have these really small emission regions further out, I think.
Thanks, Kenzie and Jacco.
Yeah.
Ollie?
Yeah, thanks, Kenzie, for the talk. I was wondering, do you think at this point we can already start ruling out other sources as being, or other objects as being the source of FRB emission, as so many things point to magnetars? Do you still think there's some place for other objects as FRB sources?
I'm not sure we can do that because here, at least, it looks like potentially magnetic reconnection is where the energy is coming from, and how the energy is harnessed from the magnetic field. But you see magnetic reconnection in a lot of different areas of astronomy. So yeah, I don't know if you can necessarily rule out different objects just based on this. I think you have to combine both where it's located. So here it's in a globular cluster, for example, and what types of objects are usually found in globular clusters, with the fact that it looks like Crab pulsar and the galactic magnetar, to come to some conclusion about what the progenitor is.
Thanks, Kenzie.
Okay.
Thank you.
So that wraps up our questions for Kenzie, as far as I can see. There has been some discussion in the chat as well. And I want to thank all the speakers here, the ones from the second half. So that's Valentina, Paul, David, Deepak, Nadia, and now Kenzie, for great talks, for keeping on time. And of course, I want to thank the audience for engaging with the speakers in questions. That wraps up this session for now. So I want to thank everyone for joining in, and till next time.